Welcome to episode 4 of C++ Quant Dev Fundamentals. Today we'll talk about intrusive data structures and what intrusiveness really is. When people hear intrusive data structures, they often think it is some obscure C++ trick that is used only by experts. But in reality, intrusive data structures exist because standard containers don't fit well within the low latency systems. Low latency systems don't care much about average performance. They care about being predictable all the time. And one big problem is memory allocation. Allocating memory dynamically is unpredictable. Sometimes it's fast, sometimes it suddenly takes much longer because of fragmentation or allocator state. Those rare slow cases matter a lot because they show up as latency spikes. Standard containers hide allocations inside operators like insert or erase. So you don't really control when that unpredictability happens. And memory layout is another issue. Modern CPUs are heavily affected by how CPU data sits in memory and cache. If data is scattered around, the CPU wastes time waiting for memory. Standard containers often hide or change memory layout behind the scenes, which hurts cache behavior. Object lifetime is also hidden. Containers decide when objects are created and when they are destroyed. In low latency systems, however, engineers usually want full control on the objects that are created and destroyed. When are they created upfront? When are they reused? When are they moved around without being destroyed? And intrusive data structures flip that model. Now, instead of the list containing objects, the objects own itself, and the connecting part is done by the data structure. So linking and unlinking is done by the data structure. This removes the hidden work. Finally, low latency systems care most about worst case delays, not averages. Even one unexpected allocation, page fault or cache miss, as we saw in the previous video, can ruin performance guarantees. Intrusive data structures reduce these risks by avoiding allocations and keeping operations simple and at fixed cost. They are not about being clever. They are about controlling memory, lifetime, and predictability, which is why they are common in trading systems, real-time software, and other performance-critical systems. Let's start with what C++ normally does, because on the surface it looks completely reasonable. You write something like std list orders order.pushback order. Nothing about that code feels dangerous or expensive. But under the hood, several things happen that matter a lot in low latency systems. First, the order object is either copied or moved into the container. Then a separate heap allocation is performed to create that list node that will hold that object. That node becomes owned by the container, not by your code. And from that point, the container is responsible for managing the object's lifetime, deciding when it is constructed, when it is destroyed, and when its memory is released back to the allocator. Conceptually, every mainstream implementation ends up looking like a data structure with two pointers and the value embedded inside, where each node lives at some arbitrary location in memory. But the crucial observation is that the container knows, owns both node and memory here. And that single ownership decision can have far-reaching consequences because it will introduce some allocator jitter, because every insert or erase can trigger some unpredictable allocator behavior. It will lead to memory fragmentation as nodes are allocated and freed over time. It will create some unpredictable latency because allocation and deallocation costs will vary, and it will then create ownership transfers inside container operations, making it hard to reason about when memory and lifetime changes actually occur. Whereas an intrusive data structure completely changes who is in control. When we say that a data structure is intrusive, what do we really mean? What we mean is that the container does not own the elements at all. The container does not allocate memory for them, does not destroy them, does not decide when their lifetime begins or ends. Instead, the elements themselves carry information needed to be linked into a data structure. In the standard container model, you have a clear separation between the value and the node that stores it. The container creates a node, puts your object inside it, and manages the node's lifetime. But in an intrusive structure, that separation disappears. The object itself becomes the node, and that kind of contains the pointers that allow it to participate in the list, queue, or other structure. There is no need of a wrapper or any hidden layer, and no extra allocation sitting between your data and the structure that orders it. So instead of thinking in terms of a list node that happens to store an order, you think in terms of an order that happens to be linked into a list. That distinction is subtle, but it is extremely important. The container becomes little more than a set of rules for how pointers are connected and disconnected. It no longer owns memory, it no longer creates objects, and it no longer destroys them. Its job is reduced to pure pointer manipulation. And because of this, operations like insertion, removal, or reordering become extremely cheap and predictable. Inserting an element does not move data around. It does not allocate memory. Reordering of elements does not move data around. Removing an element does not free the memory. All of these operations boil down to a fixed number of pointer writes that will always touch the same known memory locations. There are no allocator calls, no surprises, and no variability hidden behind some sort of abstraction boundary. This also means that the ownership and lifetime are explicit, right? Not implicit. The objects are typically created ahead of time, often in pools or arenas. And if you see, objects are reused throughout the lifetime of the system. The data structure merely reflects the current logical ordering or state of those objects. When an object leaves a list, uh, it doesn't disappear, it simply stops being linked. When it creates another structure, it is linked again. The object's memory never moves unless you explicitly move it. This inversion of control is the key idea behind intrusive data structures. So if you look at this smallest possible intrusive list, right, stripping everything down to the absolute essentials so we can clearly see what is going on. At the core of any linked structure is a node. And in an intrusive design, that node is not something separate, it is something that lives inside the object itself. So to represent that idea, we start with a very small structure that contains only two pointers, one pointing to the previous node and the other pointing to uh, the next one. There is no value here, there is no payload, there is no ownership logic. It's just the links that need to participate in a list. This structure is intentionally minimal because its sole purpose is to enable linkage, nothing more. Once we have this node, we can build a list around it. Notice what immediately stands out. The list itself does not allocate memory, it does not create nodes, it does not destroy nodes. It simply keeps a track of where the list starts and where the list ends. Node head, node tail, equal to null PTR as of now. So the list is just a small piece of logic that knows how to connect or disconnect nodes that already exist somewhere else in memory. So the push front is taking intrusive node pointer in, and remove is also taking an intrusive node pointer in. So it is already referring, or it's already taking a reference to the location that is already there in the memory. It's not doing anything inside. So if you look at the uh, once we have this intrusive node, node prev and node next, we can build a list around it, right? When we push a node to the front of the list using push front, all we are doing is rewiring pointers. The new node's next pointer is set to the current head. If a head already exists, we update its prev to point back to the new node, and if the and then we update the list's head pointer. If the list was previously empty, we also set the tail pointer, right? No allocation happens here, no constructor called, no memory requested. The operation always performs the same number of small fixed memory pointer writes. Removing a node in this function does the same thing. we carefully reconnect the neighboring nodes so that they skip over the node that is being removed. And then if the node was at the head or tail, we update those pointers accordingly. Finally, we clear the node's own pointers to signal that it is no longer part of the list. Again, nothing is allocated, nothing is freed, no object is being destroyed. The node simply stops being linked. And that is the entire data structure. There are no templates, no allocators, no exceptions, and no hidden work happening behind the scenes. Every operation is visible, explicit, and bounded. You can count exactly how many pointer writes occur. You can predict exactly which memory locations are touched. This simplicity is not accidental. It is the reason why intrusive lists exist. By reducing the data structure to pure pointer manipulation, we eliminate the entire classes of unpredictability and make the behavior deterministic. In low latency system, this kind of simplicity is not a limitation; it is a feature, right? So, why do intrusive lists exist in trading systems? Because of the way real trading systems actually work, not the way data structures are taught in textbooks. In a live trading system, orders do not magically appear inside containers. They already live somewhere. An order is usually created from a pre-allocated arena or object pool or fixed array long before it is ever linked into an order book. So we will need that pre-allocated arena address in which this push front is taking that intrusive node pointer, right? Uh, it is already there long before it is ever linked into an order book or strategy state. This is done deliberately so that the memory is reserved upfront and never touched again during trading hours. And once the market opens, the system must operate without surprises. You do not want memory allocation, page faults, or cache miss or allocator lock showing up while handling market data. And because of this, you never want a container to decide an object's lifetime, right? The second point. In standard containers, inserting an element uh, implicitly constructs it, and erasing it implicitly destroys it. In trading systems, that model is backward. An order might need to move between multiple states, pending, active, modified, cancelled, without being destroyed or reallocated. Lifetime is like a business decision, not a container decision. And intrusive lists respect that reality by letting the order exist independently of any data structure that happens to reference it. Another critical requirement is the constant time reordering. In real markets, orders are constantly being promoted, demoted, or removed based on events like fills, partial fills, cancels, and priority changes. These operations must always be big O of 1, not just on paper but in terms of actual instructions executed and memory touched. Intrusive lists allow promotion, demotion, uh, etc. to be implemented as a small fixed number of pointer updates. No iteration, no copying, no reallocation, etc. And that predictability is essential when you're processing hundreds of thousands of events per second. And lastly, you want zero allocations on hot paths. It is not an optimization choice, it is a requirement. In high frequency trading systems, even a single unexpected allocation can cause a latency spike of tens or hundreds of microseconds. So that spike might happen once in a million operations, but that is enough to lose trades or violate latency budgets. And intrusive lists completely remove this risk by design. If the system is correctly built, allocation simply does not exist on the critical path. And because intrusive lists only rewire the pointers on objects that are already in memory, they provide your deterministic latency. Every operation touches a known small set of memory locations. So there is no hidden behavior, and the ownership is sort of explicit. The system um, the system knows exactly who owns and the object when it will be used. Memory layout is cache aware because orders are often allocated contiguously in pools, improving the locality and reducing the cache and TLB misses that we saw in the previous video. Even failure modes are predictable. If something goes wrong, it will happen in known places, not deep inside some memory allocator, right? So the failure modes need to be predictable. This is why intrusive structures are not unique to trading. Operating systems kernels use them, right? Because they cannot afford unpredictable latency while scheduling tasks or handling the interrupts. And game engines, they use them because frame deadlines are absolute. A single allocation at the wrong time can cause some visible stutter, right? High frequency trading systems use them for um, the same fundamental reasons. Missed deadlines will cost money, and intrusive lists are simply the data structure expression of the broader principle shared by all these systems. Take control of memory, take control of lifetime, take and eliminate the uncertainty wherever possible. Intrusive data structures are powerful, but they are not free of any limitations, right? Pretending otherwise is a mistake. They trade convenience for control, and that trade only makes sense when control genuinely matters. One real cost uh, is that objects become tied to the structure they participate in. When an object embeds linkage pointers, it is no longer a clean standalone value. It carries a structural state with it. That means the same object cannot easily belong to two different lists at the same time unless you explicitly design for it. It makes the code very cumbersome, often by embedding multiple link fields. This will add complexity and require careful planning. And another cost is that ownership becomes harder to reason about, not easier. In standard containers, ownership is clear. You give the container to own, they do everything with it. In intrusive structures, ownership lives elsewhere, often in pools or arenas or long-lived arrays. Like as I said, the structure is something that should not die or keep constructed. That ownership is decided by some other pool. They just need you to effectively move that structure into pending, completed, those kind of states, right? So that needs to be done in microseconds or nanoseconds. And with just merely references to those objects, the programmer must be disciplined about ensuring that the objects are not destroyed while still linked, or not reused prematurely, or not accidentally left in an inconsistent state. And bugs here tend to be subtle and severe: dangling pointers, double removals, or corrupted lists that don't fail immediately but surface under load. Those kind of things happen, which can be cumbersome to deal with. And intrusive data structures also require more discipline from the engineering team, right? Um, there are fewer guardrails. You cannot rely on RAII, resource allocation alone, to save you. You must establish and follow strict invariants. When objects are created, when they are linked, when they are unlinked, and when they are recycled, that this is where intrusive structures are usually paired with strong conventions, careful code reviews, and extensive assertions in non-production builds. Without that discipline, intrusive designs can become fragile. The whole point of starting quant dev or HFT dev is to think in terms of intrusiveness. Stop using default systems and uh, take control, take ownership of all the allocations and memory. And for that, you will need discipline. There is also the practical downside of reduced STL compatibility. Right? Intrusive structures don't plug cleanly into algorithms. Expect the standard iterators or container semantics. You give up some composability and convenience. Many useful generic utilities simply don't apply, and you often end up writing more custom code. For general application development, this cost is rarely worth paying. But in low latency systems, these costs are often acceptable and even necessary because the alternative is worse. In a trading system, missing a latency target by a few microseconds during market spike can mean lost trades, right? In such an environment, convenience abstractions that hide allocation, lifetime, and memory layout are liabilities. Engineers have to choose the intrusive data structures not because they enjoy that kind of complexity, but because they cannot afford unpredictability. and when the system must behave the um, same way at 9:30:0:00 or at 15:59 something under extreme load, control will beat convenience. And that is why intrusive structures persist in kernels, in game designs, in HFT systems, despite their complexity. These domains accept higher engineering discipline in exchange of something that is far more valuable: bounded behavior, exp explicit ownership, and predictable performance when it matters more. So now that we understand what intrusiveness necessarily means, we can do something concrete, right? We can try to ourselves implement an intrusive list and a normal list and benchmark some of it. We can do something concrete. We'll implement the behavior the usual way and then the intrusive way, and compare instruction by instruction, line by line, cache line by cache line, and we'll measure where the time actually goes, how memory is touched, and what that means for latency. That is exactly what the next video is all about, turning something what we just learned into something measurable. Stay tuned. Thanks for watching.